including real mode, on these CPUs. X86 mode and 32-bit protected mode are added, with additional instructions provided in these modes to manage their features. SMM, with some of its own special instructions, is available on some Intel i386SL, i486 and later CPUs. Finally, in long mode, AMD SMM, with some of its own special instructions, is with a computer running UEFI, the UEFI firmware, X86 and legacy option ROM, the UEFI boot.
I did it again. I was sleepy and clicked the mouse. We have to read page by page. Sorry for that. That's because I'm always used. I have my fingers on the mouse button, and when I get sleepy or tired, I click by mistake. I don't know why, but I do that. I always forget not to do it. Read only this page.
8088, 80,186, 80,188, and 80,286. These instructions are available in real mode on all X86 processors, and in 16-bit protected mode, 80,286 onwards. Additional instructions relating to protected mode are available. On 80,386 and later, 32-bit instructions, including later extensions, are also available in all modes, including real mode, on these CPUs. X86 mode and 32-bit protected mode are added, with additional instructions provided in these modes to manage their features. SMM, with some of its own special instructions, is available on some Intel i386SL, i486 and later CPUs. Finally, in long mode, AMD Optron onwards, 64-bit instructions, and more registers, are also available. The instruction set is similar in each mode, but memory addressing and word size vary, requiring different programming strategies. The modes in which X86 code can be executed in are real mode, 16-bit, 20-bit segmented memory address space, meaning that only 1 megabyte of memory can be addressed actually, slightly more, direct software access to peripheral hardware, and no concept of memory protection or multitasking at the hardware level. Computers that aspire start up in this mode. Protected mode, 16-bit and 32-bit, expands addressable physical memory to 16 megabytes and addressable virtual memory to 1 gigabyte. Provides privilege levels and protected memory, which prevents programs from corrupting one another. 16-bit protected mode, used during the end of the DOS era, used a complex, multi-segmented memory model. 32-bit protected mode uses a simple, flat memory model. Long mode, 64-bit, mostly an extension of the 32-bit, protected mode, instruction set. But unlike the 16 to 32-bit transition, many instructions were dropped in the 64-bit mode. Pioneered by AMD. Virtual 8086 mode, 16-bit, a special hybrid operating mode that allows real mode programs and operating systems to run while under the control of a protected mode supervisor operating system. System management mode, 16-bit, handles system-wide functions like power management, system hardware control, and proprietary OEM-designed code. It is intended for use only by system firmware. All normal execution, including the operating system, is suspended. An alternate software system, which usually resides in the computer's firmware, or a hardware-assisted bugger, is then executed with high privileges. Switching modes. The processor runs in real mode immediately after power on, so an operating system kernel, or other program, must explicitly switch to another mode if it wishes to run in anything but real mode. Switching modes is accomplished by modifying certain bits of the processor's control registers after some preparation, and some additional setup may be required after the switch. Examples: with a computer running legacy BIOS, the BIOS and the bootloader is running in real mode, then the 64-bit operating system kernel checks and switches the CPU into long mode and then starts new kernel mode threads running 64-bit code. With a computer running UEFI, the UEFI firmware, except CSM and legacy option ROM, the UEFI bootloader and the UEFI operating system kernel is all running in long mode. Instruction types. In general, the features of the modern X86 instruction set are a compact encoding, variable length and alignment independent, encoded as little endian, as is all data in the X86 architecture. Mainly one address and two address instructions, that is to say, the first operand is also destination. Memory operands as both source and destination are supported, frequently used toriad /right stack elements addressed using small immediate offsets. Both general and implicit register usage, although all 7, counting EP, general registers in 32-bit mode, and all 15, counting RBP, general registers in 64-bit mode can be freely used as accumulators or for addressing. Most of them are also implicit liased by certain, more or less, special instructions. Affected registers must therefore be temporarily preserved, normally stacked, if active during such instruction sequences. Produces conditional flags implicitly through most integer ALU instructions. Supports various addressing modes including immediate, offset, and scaled index but not relative, except jumps, introduced as an improvement in the X86-64 architecture. Includes floating point to a stack of registers. Contains special support for atomic read modify write instructions, XCHG CMP XCHG /CMP XCHG 8B, ZAD, and integer instructions which combine with the lock prefix. SIMD instructions, instructions which perform parallel simultaneous single instructions on many operands encoded in adjacent cells of wider registers. Stack instructions. The X86 architecture has hardware support for an execution stack mechanism. Instructions such as push, pop, call and ret are used with the properly set up stack to pass parameters, to allocate space for local data, and to save and restore call return points. The ret size instruction is very useful for implementing space efficient and fast calling conventions where the callee is responsible for reclaiming stack space occupied by parameters. When setting up a stack frame to hold local data of a recursive procedure, there are several choices. The high-level enter instruction, introduced with the 80,186, takes a procedure nesting depth argument as well as allocal size argument, and may be faster than more explicit manipulation of the registers, such as push, BP, move BP, SP, sub SP, size. Whether it is faster or slower depends on the particular X86 processor implementation as well as the calling convention used by the compiler, programmer or particular program code. Most X86 code is intended to run on X86 processors from several manufacturers and on different technological generations of processors, which implies highly varying microarchitectures and microcode solutions as well as varying gate and transistor level design choices. The full range of addressing modes, including immediate and base and offset, even for instructions such as push and pop, makes direct usage of the stack for integer, floating point and address data simple, as well as keeping the ABI specifications and mechanisms relatively simple compared to some RISC architectures. require more explicit call stack details. Integer ALU instructions. X86 assembly has the standard mathematical operations, add, sub, mul, with IDIV. The logical operator SAND, or XOR, NEG, bit shift arithmetic and logical, SAL /SAR, SHL /SHR, rotate with and without carry RCL /RCR, roll /RAW, a complement of BCD arithmetic instructions, AAA, ARD, DARA and others. Floating point instructions. X86 assembly language includes instructions for a stack-based floating point unit, FPU. The FPU is an optional separate coprocessor for the 8086 through the 80386. It was an on-chip option for the 80486 series, and it is a standard feature in every Intel X86 CPU since the 80486, starting with the Pentium. The FPU instructions include addition, subtraction, negation, multiplication, division, remainder, square roots, integer truncation, fraction truncation, and scale by power of 2. The operations also include conversion instructions, which can load or store a value from memory in any of the following formats: binary codedecimal, 32-bit integer, 64-bit integer, 32-bit floating point, 64-bit floating point or 80-bit floating point. Upon loading, the value is converted to the currently used floating point mode. X86 also includes a number of transcendental functions, including sine, cosine, tangent, arctangent, exponentiation with the base 2 and logarithms to bases 2, 10, or e. The stack register to stack register format of the instructions is usually FOP ST, ST, N, or FOPST, N, ST, where ST is equivalent to ST, 0, and ST, N, is one of the 8 stack registers, ST, 0, ST, 1, ST, 7. Like the integers, the first operand is both the first source operand and the destination operand. Sub and div should be singled out as first swapping the source operands before performing the subtraction or division. The addition, subtraction, multiplication, division, store and comparison instructions include instruction modes that pop the top of the stack after their operation is complete. So, for example, FAD ST1, ST performs the calculation ST1 equals ST1 plus ST0, then removes ST0 from the top of stack, thus making what was the result in ST1, the top of stack in ST0. SIMD instructions. Modern x86 CPUs contain SIMD instructions, which largely perform the same operation in parallel on many values encoded in a wide SIMD register. Various instruction technologies support different operations and different register sets, but taken as complete whole, from MMX to SSE 4.2, they include general computations on integer or floating point arithmetic, addition, subtraction, multiplication, shift minimization, maximization, comparison, division or square root. So for example, pad mm0, mm1 performs 4 parallel 16-bit, indicated by the W, integer adds, indicated by the pad, of mm0 values to mm1 and stores the result in mm0. Streaming SIMD extensions or SSE also includes a floating point mode in which only the very first value of the registers is actually modified, expanded in SSE2. Some other usual instructions have been added, including a sum of absolute differences, used for motion estimation in video compression, such as is done in MPEG, and a 16-bit multiply accumulation instruction, useful for software-based alpha blending and digital filtering. SSE, since SSE 3 and 3D now. Extensions include addition and subtraction instructions for treating paired floating point values like complex numbers. These instruction sets also include numerous fixed subword instructions for shuffling, inserting and extracting the values around within the registers. In addition, there are instructions for moving data between integer registers and XML, used in SSE/FPU, used in MMX, registers.memory instructions. The X86 processor also includes complex addressing modes for addressing memory with an immediate offset, a register with an offset, a scaled register with or without an offset, and a register with an optional offset and another scaled register. So for example, one can encode move X, table and X and DC*4, as a single instruction which loads 32 bits of data from the address computed as table and X and DC*4, offset from the DS selector, and stores it to the X register. In general, X86 processors can load and use memory matched to the size of any register it is operating on. The SIMD instructions also include half-load instructions. Most 2-operand X86 instructions, including integer ALU instructions, use a standard addressing mode but 11, often called the modreg R/M byte. 12, 13, 14. Many 32-bit X86 instructions also have a SIB addressing mode byte that follows the modreg R/M byte. 15, 16, 17, 18, 19, in principle, because the instruction opcode is separate from the addressing mode byte. Those instructions are orthogonal because any of those opcodes can be mixed and matched with any addressing mode. However, the X86 instruction set is generally considered non-orthogonal because many other opcodes have some fixed addressing mode. They have no addressing mode byte, and every register is special. 19, 20. The X86 instruction set includes string load, store, move, scan and compare instructions, LODs, stas moves, SCAS and CMPS, which perform each operation to a specified size, B for 8-bit byte, W for 16-bit word, D for 32-bit double word, then increments /decrements, depending on DF, direction flag, the implicit address register, SI for LODs, DI for stas and SCAS, and both for moves and CMPS. For the load, store and scan operations, the implicit target /source /comparison register is in the L, AX or X register, depending on size. The implicit segment registers used are DS for SI and S for DI. The CX or X register is used as a decrementing counter, and the operation stops when the counter reaches 0 or, for scans and comparisons, when inequality is detected. The stack is implemented with an implicitly decrementing, push, and incrementing, pop, stack pointer. In 16-bit mode, this implicit stack pointer is addressed as SS_SP, in 32-bit mode it is SS_ESP, and in 64-bit mode it is RSP. The stack pointer actually points to the last value that was stored, under the assumption that its size will match the operating mode of the processor, i.e., 16, 32, or 64 bits. To match the default width of the push /pop/call/ret instructions. Also included are the instructions enter and leave UHIC reserve and remove data from the top of the stack while setting up a stack frame pointer in /ek/RBP. However, direct setting, or addition and subtraction to the SP/ESP/RSP register is also supported. So the enter/leave instructions are generally unnecessary. This code in the beginning of a function, push ep, save calling functions stack frame, ep. Move ep, ESP, make a new stack frame on top of our caller's stack. Sub ESP, 4, allocate 4 bytes of stack space for this function's local variables. Is functionally equivalent to just enter 4, 0.